Hello everyone. In the today's video we will be discussing about the current equation of the MOSFET. That is, in the previous video we discussed about the derivation for the current equation for the MOSFET in the linear region as well as in the saturation region. So finally in the saturation region we come across the equation which is mu n COX by 2 W by L into VGS minus VTH whole square, right? So this is the saturation current equation what we have come across in the previous video. So here in this there are certain terminologies that we have to come across. One of it is Kn dash, which is mu n COX. So this mu n COX is basically called as process transconductance. Process transconductance, as this mu n is the mobility of the electrons and COX is epsilon OX by TOX. So these are the parameters which are dependent upon the fabrication process. So this mu n COX is hence called as the process transconductance. And here we have another parameter called as Kn, which is Kn dash into W by L. Okay, so which is Kn dash into W by L. So this is called as device transconductance. Device transconductance. So here along with the process transconductance you have W by L, which defines the dimension of the MOSFET. So here we are going to define our own W by L according to the device, W by L of the MOSFET device, hence it is called as the device transconductance. So here the ID equation happens to be Kn by 2 into VGS minus VTH whole square, or it is basically Kn by 2 into VOV square, right? So if I derive this, differentiate this current equation, say for example this is the 8th equation in the continuing with the previous video. So if I differentiate equation 8 with respect to VGS, okay, so here in this equation ID is equal to mu n COX by 2 W by L into VGS minus VTH whole square. So if I differentiate here with respect to partial differentiate with respect to VGS, so here we have only VGS as a variable, so basically x minus t whole square, which is differentiation of x minus t whole square will be 2 times of x minus t into differentiation of x will be 1. So this is mu n COX by 2 into W by L into 2 times of VGS minus VTH into differentiation of VGS is 1. So this and this cancels. So this happens to be mu n COX into W by L into VGS minus VTH. So this is nothing but ID divided by VGS, which is nothing but transconductance given by GM. So GM represents the transconductance. So we also have the current equation in the linear region, which is mu n COX W by L into VGS minus VTH minus VDS by 2 into VDS. So this is the linear current equation, okay, and what we have processed now is basically the saturation current equation, right? This is VDS and ID. So basically we determine the transconductance in this region. Okay, so here for the linear region, what happens for the small value of VDS, the VDS will be small for compared to the VDS value in the saturation region. So what we do here, we will neglect this and this mu n COX W by L into VGS minus VTH into VDS. Okay, so this is ID. So if I differentiate this with respect to VDS, that is output voltage, by the VDS, so we have only VDS as the function and the remaining term will be constant, hence this what we have ID by VDS, which is nothing but GDS, happens to be mu n COX W by L into VGS minus VTH. This is again the same, where GDS is the output conductance so 1 upon GDS will give you RDS, output resistance. So this RDS is the output resistance for only in the linear region, okay, whereas in the saturation region it happens to be output resistance, which we will discuss it shortly. Okay, so this is the output resistance corresponding to the MOSFET working in the linear region, that is only for the small value of VDS. Small value of the VDS we have neglected here in this, whereas here this is the transconductance. Okay, the transconductance, whereas the expression remains same for both, but doesn't mean that both are one and the same. Whereas here in this the VDS value is very large, whereas here in this the VDS value will be very small again. Okay, so again continuing the same equation, we will see the effect of the output output voltage further to find the channel length modulation. That we will continue it in the next class. Okay.